Hi, I'm an old guy and I do maths. And the task ahead of us today is to find the inverse of these two functions, y equals x to the 3, y equals x to the 4, to graph the new functions and figure out whether they intersect, and if so, where they intersect. Finding the inverse is fairly straightforward. I've done it here in full for y equals x to the 3, so let's just go through those steps. The first thing that you do is you swap the x and the y, so you wind up with something that looks like this. And what we want to do is we want to get y down to just itself, y to the power of 1. So in order to do that, we take the third root of each side. And we wind up with the third root of x is equal to y, which we can rewrite in this index form, given that we were originally set this in index form, put it back in index form. Now the same process holds true for x to the 4, so I've just cut to the chase here. The one thing I want to say about x to the 4, which makes it different from x to the 3, is that the domain and range of x to the power of 3 include all numbers from negative to positive infinity. Now that's not the case with x to the power of 4. The range is restricted to positive real numbers and 0. Now that's important when it comes to drawing and in fact dealing with the inverse of that. Now people who know about inverses will know that when you find the inverse of a function, the domain and the range swap around. So in this case, we have a restricted range. It is from 0 to infinity, or all positive real numbers, including plus 0. Therefore, the domain of this function is going to equal the range of this. So we're not going to have any negative values here. Simple as that. Why are we not going to have any negative values? Well, if these numbers are from 0 to positive infinity, anything raised to an even power is going to turn out as a positive number. Okay, let's get to work. Actually, in fact, any number, any real number, positive or negative, is going to turn out as a positive number if you raise it to the power of 4. What does this pair of graphs look like? Well, I've done the drawing here because it saves time. What I initially did was I subbed in 0 and 1 to both of these functions, and I got 0 and I got 1. 0 to the power of 1/3 is 0. The third root of 0 is 0. The third root of 1 is 1. I'll just put that value there, that's 1 and that's 2. The fourth root of 0 is 0, the fourth root of 1 is 1. Where things begin to differ is after 1, on the right hand side anyway. Now if I continue the function y equals x to the power of 1/4, I'm looking for something that I know the fourth root of, just quickly to get a point on this Cartesian plane. So I chose 16. The fourth root of 16 is 2. If I come back to 8 and take the third root of 8, I get 2. So you can see that these two graphs have started to diverge. And if I were to continue the red graph, it would head off in that direction. They would continue to diverge. Now it's a little hard to see, but this graph here, this y equals x to the power of 1/4, only exists from 0 through all the positive real numbers. This graph here, y equals x to the power of 1/3, exists for -1 and obviously -8 and onwards through to negative infinity. So that bears out what I was talking about earlier on, that the domain of this function is restricted because the range of this function was restricted. Okay, so we have our points of intersection there and there, and we've got that by just subbing in. Now your teacher, if your teacher were looking over your shoulder, could accuse you of being lucky or just using trial and error. So I'm going to have a very quick look at how we find these values algebraically. So let's get to that. Okay, so we'll start off with x to the power of a quarter equaling x to the power of a third. That's what we want to find. We want to find where this is. And what I'm going to do is I'm going to rearrange this very slightly. X to the power of 1/3 minus x to the power of 1/4. That should work. And I'm going to raise that to the power of 12. And what I'm going to get from that is x to the power of 4 minus x to the power of 3. Now, if we bear in mind that up here we had this equaling this, I can say that this equals 0. And that is really, really handy because we can factorize this, and we can factorize this really easily. Take out the common factor, x to the power of 3, and we're left with x minus 1 equals 0. And that gives us solutions of x equals 0 for this, and x equals 1 for this. And those are the points that give us the points of intersection of these two graphs. And that's how you do that. Okay, well, I hope that was useful and helpful. I hope that this improves your understanding of how to do inverses and how to find solutions for where they intersect. If you did find this useful, please like and subscribe, and I'll see you next time. Bye.